Hello, everybody. Hello. Welcome to the Architectural Foundation of Santa Barbara. My name is Greg Reck. I'm president of the Architectural Foundation, and I want to thank you for attending. Thank you for attending our lecture series, which is in commemoration of the 100th anniversary of the 1925 earthquake, which occurred on June 29th, 1925. So the last Sunday in June here. I'd like to remind everyone to please turn off your phones. Maybe what you were doing. Yeah. So if you wouldn't mind, turn your phones to silent. And I want to thank our lecture committee, Cass Ensberg, raise your hand, and Suzanne Tejada, probably still out on the porch. She was the one that was checking people in. They're our co-chairs. And then Barbara Burkhart, Ann Dwelly, right here, and then Lydia Rayo, our executive director. So our lecture tonight is Why Buildings Fell by Structural Engineers Sage Shingle. And then following tonight's lecture, we'll have a Q&A session with Sage. And then after that, I invite you all out to our back patio here for wine and desserts provided by the Berryman. And then next Thursday night will be our final lecture in the series, and that's going to be by historian, author, and AFSB board member Betsy Green, who is sitting right here. And she's going to share stories of earthquake survivors. And it's stories told by the survivors that she's gleaned through newspaper accounts and also with interviews from their descendants. And then in the fall, we plan to do some additional lectures, and Betsy's going to do a lecture on how to research the history of your home. And as most of you probably know, Betsy researches and writes The Great House Detective, which are featured in The Independent. Another lecture for the fall is going to be Sherry Ray, who gave our first two lectures, and she's going to present a part 3 on what would Pearl do. And so what would Pearl do if faced with the challenges that the city is facing right now? And so look for that in the fall. If you are not signed up for our email list, please go ahead and see Suzanne after the lecture and get your name on a piece of paper, and we'll let you know when those are happening. Other events that we've had to commemorate the earthquake, as you see on our gallery walls, is a show called Gimme Shelter by Marcia Rickard. And examples over here are natural disasters, and then over here on this wall mainly are man-made disasters. And then last for our events, this Monday through Friday, June 23rd through 27th, we're giving walking tours in the evening. They begin at 6 p.m. and they're going to cover a lot of the buildings that were built following the earthquake, and we'll have photos of what the buildings looked like just shortly after they were damaged to supplement the tour. And again, that's Monday through Friday, June 23rd through 27th at 6 p.m. And we meet on the Anapamu Street side of the public library. Okay, so our speaker tonight, Sage Shingle, is both a professional engineer, professional civil engineer, and a licensed structural engineer. And Sage works with T&S Structural. Sage is going to offer insights into why buildings fell during the 1925 earthquake using simple, everyday language and diagrams, right? He's promised. Diagrams and then historic photographs. So he's going to share key reasons as to why parts of many of the buildings fell during the 1925 earthquake and the lessons learned since then. So Sage grew up in Santa Barbara from the time he was 5 years old and attended Cal Poly San Luis Obispo to study structural engineering. And his career has spanned the West Coast from Southern California to Seattle. As I mentioned just a minute ago, he's earned both professional civil engineering and structural engineering licenses and has over 20 years experience with structural analysis, design, and project management. His experience includes a wide variety of building types, including educational institutions, public community centers, healthcare facilities, and residences. And he has a passion for teaching in both the office and through his involvement with a nationwide ACE mentor program, which is for local high school students interested in the profession of architecture, construction, and engineering, ACE. So again, following Sage's lecture, we're going to have a Q&A session, and then I invite you to join us out back for treats by the Berryman and wine. All right, then I'll turn it over to you, Sage.
All right, thanks, Greg. He mentioned there's no equations in this, but there is, I think, one. We're going to gloss over it for the most part. But a couple quick points of clarification on this. There's a ton of smart people that went into the background of this, right? I'm going to mention a couple, but there's so many people that have been involved in so many levels, so many years. So I'm going to just mention a couple, but that's it. There's so many. Another thing here, I need one quick volunteer. Super strong. First hand. That was the first hand. Okay. So this is just a block of stone. You just have to hold it over your head for a little while. You can actually like hold on, like just verify that it's heavy. Let the crowd know. It's pretty heavy. It's pretty heavy. It's 50 pounds. I actually weighed it last night.
Oh, is that all?
That's all. So that's gonna come in be important later in the show. We do have a bunch of slides to get through, so we'll try to not linger a bunch at stuff. Otherwise, we'll be here for like 3 hours. But there's a ton of interesting stuff. I try to condense as much as possible. But here's the basic outline. We're going to just set the stage. So we're going to learn about earthquake engineering. We're going to learn about earthquakes. And then we're going to talk about like the bread and butter of why we're here, the main event, looking at pictures of the 25 earthquake and why things failed, what went into it. And then we're going to kind of follow up on how we're doing things different, what earthquakes have taught us over the years, and how we've evolved our building code to really become better engineers. So Greg told basically a little about me, but I grew up here in Santa Barbara. Been doing engineering for quite a bit. Feel lucky that I kind of stumbled into something I really like to do. We all probably have hopefully a similar story, but yeah, and here's my family. Spend a lot of time with them. Okay, so setting the stage. I like to think of structural engineering as an epic battle between man and nature. You can replace my earthquake with a tsunami, a windstorm, whatever it is. Nature's trying to, we're trying to build things, and nature's, kind of trying to prevent us. Here's the first of the smart people. We probably all know this guy. I didn't before we started here. He had the hypothesis about continental drift and is really the basis of what our seismic engineering and the understanding of faults and movement of the earth is all about. So earthquakes, how do they happen? We know that the earth is composed of the mantle, the crust, plates are moving, and so if you can think of plates kind of moving as we all started with Pangea and we're moving out from there, you can kind of interlock your knuckles like that and think of plates shifting as trying to shift across the knuckles. So as plates move, that's what causes our earthquakes. So as your knuckles, I don't see anybody doing it, just to make sure I'm right. There's one. So the rock is all interlocked, right? And so it builds up stress as one plate's trying to move by the next one. There's a buildup of stress, eventually gets released in an earthquake. So we know that there's fault planes all over the world, and there's actual plate lines. The plate line here close to us is the San Andreas Fault. So we're obviously right here. So maybe somebody's heard that in 10 million years, Los Angeles and San Francisco will be neighbors. So we're moving north because we're on the Pacific plate here, moving that way, versus San Francisco going that way. So how do we know where earthquakes kind of started? So there's two kinds of waves that earthquakes produce. P waves, which is just primary waves. So P is primary, super simple. And then S waves. So P waves, S waves are the secondary waves. Again, super simple. But P waves kind of expand and contract or pull the soil kind of like a slinky. My son told me that when I was telling him about this last night. So pulling a slinky and pushing a slinky and expanding it. And then S waves, kind of move the earth sideways and up and down. So P waves are actually, if a P wave is faster than an S wave, which is actually an important thing. So P waves, if it takes from an earthquake, if it takes 10 seconds to get to you from a P wave, it takes 6 seconds, for a P wave to get to you. It takes about 10 seconds for the S waves to get there. So there's a little bit of lag between when the first waves get there and the second waves get there. And the second waves are the ones that cause the majority of the damage. So here's, seismograph is basically a measurement of how those waves are hitting, the site. So you get your first primary waves come through, and then the secondary waves, and you start to get a big jolt. So that's kind of how we actually started to have seismometers and across kind of the West Coast, and then we can triangulate, knowing how long it took, an earthquake to get to this point from this registry to same thing from this, and we can kind of figure out where it actually came from. It's super technologically advanced now, but that's the basis of it. And that P wave versus S wave, so the primary versus the secondary, is actually something that we're now using to provide a slight early warning. So there's now you can go to, California's, earthquake website and find, an app that you can download, and it'll give you a warning similar to like fires that we're doing now. And so it's not a predictor, right? It's not going to predict that we're going to have an earthquake in San Fernando in 2 days. It's a quick reaction, but it's the thought is this, because seconds matter, right? So if you can get a 5-second lead and be able to get to somewhere safe, then it may make a difference. So earthquakes, all earthquakes have a magnitude. This is what we're all familiar with, right? So when you hear an earthquake, you think, how big was it? So that's the Richter scale, the moment or the magnitude of the earthquake. That's how strong the earthquake is, and how much force it produces, how much force it generates. And then all earthquakes have intensities as well. So that's actually kind of a measure of how each site feels it. So one earthquake, maybe in Ventura, has a magnitude, and that magnitude is the same regardless of where you are, but the intensity varies. So if we're close to the earthquake, we're going to feel it a lot more than if we're in San Francisco. So here's the Richter scale kind of magnitudes. You note that the Richter scale was developed in the 1930s, so it's just after our earthquake. But what's kind of big things to point out here are, one, the Richter scale's on the left, and then at this point, this is where we start to about feel earthquakes. So there's a ton of earthquakes down here daily. There's so many earthquakes that are going on constantly that we never feel, we never know about. USGS tracks them all, so you can see maps that have all of them. But there's a ton that happen all the time. Then you start to go up this, and we get to where there starts to be a bit of damage. You start to feel some shaking, like a little more so. Things might come off shelves and that sort of. And then as we go higher, obviously less earthquakes are happening, right? So it's very rare, So you get up to that point, And this is where the Santa Barbara earthquake was. So we're getting pretty high up there. That's 6.8. We're kind of jumping ahead, but a 6.8 magnitude. And then the highest value California earthquake on record is San Francisco earthquake, 1906. So that's, this is, certainly the range where there's a lot of damage and it's widespread, and there's injuries and they're pretty serious. But it's very rare to get up into this range. These are specific kind of areas of the world that have specific types of faults that tend to deliver those. And California has a lot of faults, but they aren't that kind of fault. So you don't see any of the California earthquakes kind of up in this range. One of the other things that's really interesting about this is the amount of energy released. I got a diagram a little bit later to kind of show, but basically not a lot of energy is released down here. And as you get higher and higher on this, it just gets, it's almost exponential how much energy is released on these larger earthquakes. So talking about the Richter scale still, so the older way how it was first done was basically just measuring, I saw that diagram of the, amplitude of the shaking and how big that was. They basically just would look at that and then figure out how far away the earthquake was, and that's, that's how they would kind of dictate the magnitude. So this is the one equation I worried you guys about. We're gonna just skip right over it, but the one thing that changed in the 70s essentially was that we recognized that the Richter scale could be adjusted and kind of more accurately reflect higher level earthquakes by doing this, which is the idea of an earthquake is kind of a buildup back to my knuckles, right? It's a buildup of stresses going across the knuckles. So they want to move, they build, they're getting stronger, they start to see a little bit of movement maybe, and then all of a sudden there's a release. And so that release causes that earthquake. And so there's a, area, that the earth actually shifts. So how much area that shifts is how big this earthquake is. So it's really the amount of kind of rock, soil, whatever it might be that we're shifting. So here's more on the magnitudes. So we talked about the higher you get up that, like the more energy is released, right? So just as an example, using pasta, right? So a magnitude 5 earthquake is one piece of pasta. We've all done that in the kitchen. Magnitude 6, you increase it by, multiply by a factor of 32. Don't ask me about the 32 because I don't know, actually. My son also told me to learn that, but I didn't, so I apologize. So 32, we've all probably done that in the kitchen too, right? So, but it's 32 times more energy than a magnitude 5. So then going up to a magnitude 7, so now we're talking about 32 times the already magnified 32. So we're up to 1,000 times what we started at the. So none of us have probably done this in the kitchen. Then you jump up from a 7, you go up to an 8. Now we're talking a ton of energy to try and break through. So going up to an magnitude 9, which was the very tip top of that prior diagram, right? Just every once in a while, like not often at all. I think in the like 250 years that we've been kind of tracking earthquakes, I think there's been like 15 magnitude 7 and up earthquakes in California. So that's not earth-wide, but certainly gives the idea that they're rare. So the other thing that we mentioned was the intensity. So the intensity scale. So this is hard to visualize, but basically As you go down this list, it starts to get more violent, more severe. So at the top of the list, it's, we didn't feel it. And then it increases from there. And so this is actually used by the USGS website now. And so anybody after any earthquake can kind of go in and check how they felt the earthquake. Provides a lot of information. So earthquakes, where they happen. So Ring of Fire is the circle around the Pacific Ocean, and about 80% of earthquakes year round happen along this. So here's using the United States Geologic Survey website. Anybody can go do this. So tonight, you guys, you can go and look at the, so for the last 30 days from last night, this is how many earthquakes there were that were magnitude 2.5 or above. So 2.5 was about that threshold where we said that's where you start to feel it. Right? And then in the last 30 days worldwide, number of earthquakes 4.5. So that's where you start to see some kind of minimal damage. And the color coding here is new is orange, not quite as new as yellow, and then older is white. And then the size of the dot is the magnitude. As it gets bigger, it's a bigger magnitude. So here's the West Coast, same map, just zoomed into the West Coast. Now this is all of the earthquakes in the last 30 days. This is all of the earthquakes that are feelable, right, at the 2.5 level. And this is the earthquake that it was a 4.5, so at that causing damage level. Wise man once told me that California has its faults. This is the San Andreas Fault. This is the plate boundary. So this is moving this way, this is moving this way, going past each other. And then this is actually the faults across California. So big concentration kind of along that San Andreas, but a ton kind of scattered as well. So over the years, this is, we'll see a slide a little bit later that has a little bit backed, how we used to look at earthquakes, but this is kind of a current earthquake that takes into, or a current map that takes into account how close you are to earthquakes to be able to design for an earthquake. So what these numbers are percents of gravity. So if I'm holding this, right? So I'm holding this and I'm holding 100%. Where's my volunteer again? So that's 100% of gravity, right? I'm holding that. So out in these red zones, you design an earthquake horizontally for 80% of that force. There's some other numbers behind it, but that's kind of the gist of it. And so, as you get further away from faults, we get down into smaller regions where there's not as much acceleration of the ground. So here's just a zoom in specifically to Santa Barbara. So faults are around. We're designing for big heavy forces that are amongst the biggest in the nation. If anybody remembers, this is the most recent decent earthquake in the Santa Barbara area. It was in Ojai in 2023. It was in the afternoon. I don't know what day it was, but you could feel it here in Santa Barbara. So that earthquake was a 5.1. So this, we're comparing, this is the 5.1. So the Santa Barbara earthquake that we're going to talk about is 6.8. So 5.1 to 6.1, 32 times more energy, close to 7.1, 1,000 times more energy. So, this is still at that level where you can feel damage, or you can feel the earthquake. You can see maybe a little bit of damage, but not that substantial. So this is actually from also the USGS website, and people, actually 20,000 people, logged in and registered that they felt the earthquake, and then they told the website how hard they felt it. So they use this intensity scale. So there's no reds in here, right? It's really kind of green close to the epicenter, and then blues as you filter out. But you can see that people felt it, up in the Bay Area and then down to San Diego. This is a diagram taking all those points, all those people who entered their information, and a cross-reference of how far they were away from the earthquake, right? So this is the distance from the center. So all the people closer to the center felt more shaking. This is how intense they felt it. When you get far away, and they felt it not so much. They do this for every earthquake. You go to any earthquake, and if it's big enough for people to feel, then it's in the website. So here is another kind of another diagram of it. But the cool thing about this, I think, is all these triangles. So all the triangles are actually seismometers that register and pick up the data. All the dots are people, you or me with a phone. This is just a kind of a topography map showing like how much acceleration, ground acceleration. So we talked about 100% holding. And so this earthquake generated within this kind of circle 10% of gravity accelerations horizontally, and then dissipating out from there. Okay, so here's another guy, a lot smarter than me, Isaac Newton. So Sir Isaac said, first law of motion, an object at rest tends to stay at rest. Right? Second law of motion is force equals mass times acceleration. So we talked about the mass. I'm not going to pick it up again, but we've got the mass, and so the accelerations we were just talking about in the earth, how much it shakes. So the way we're designing earthquakes or designing for earthquakes, is taking the mass of a building and then applying some horizontal loads to it, some horizontal accelerations to get the weight of the building, how fast that mass is moving, gives us a force to design for. So here's your quick 30-second how to be a structural engineer. So the earth shakes, right? Wants shake, and so the building is going to move. So this is kind of like the object at rest wants to stay at rest. It wants to stay there until the earth shifts underneath it, and now it has to catch up and move with it. So it starts to shake back and forth like that as the ground is shaking. So what we do as engineers is make sure that the floors and the roofs are tied to the walls around the building, and kind of lock them all together, so that the floor and the roof will kind of absorb the load and then redistribute it to the walls, and then the walls take it down and go back into the earth. So that's the very basics of it. There's a ton more than 30 seconds, but that gets you enough to kind of understand where we're going here later in the slides. So also talking a little bit about materials, right? So these are our typical construction materials that we'd use. Wood, everybody's been using it since we could make huts, right? Nice thing about wood is it's flexible and it can be ductile until to a point. But the bad thing about wood is big fires. So if you think about just people, moving west even, right? Settling in a town, it was first wood structures, and then we got to have some affluence, into the gold rush, and we start to get, masonry, big brick or stone buildings. Stone, a lot heavier, adobe here locally, right? And brick, so that was been common, but masonry is heavy and it's brittle, right? So if it's going to break, it's going to break, and it's going to break fast. Concrete is similar in that it's heavy and brittle, but you can reinforce concrete with steel, making it a lot more ductile and dissipate energy. Steel, we didn't have that a lot in the earthquake, but it's a material that can be ductile if it's designed the right way. Okay, so that was all the backgrounds. Here we go, main event. Looking at earthquake. So Santa Barbara earthquake was June 29th. Greg mentioned it at 6:42 in the morning, which is an important thing actually. The magnitude was 6.8, so we're pretty high up on that ramp. The intensities, here's a backed in of the intensity map that we were looking at earlier for the Ojai earthquake. So you can see, I think a lot of these are anecdotes, from individual people, right? And so there's a lot of red and orange down here in Santa Barbara, but you could see that it feels, people felt it, and there were stories about it, up to San Luis Obispo, down to Long Beach, and that probably zooms out a little bit further even. So the epicenter is 8 miles south of Mora Mesa. So you go out on Mora Mesa Bluffs, and 8 miles south of there. And then the hypocenter, which is just how deep it is, was about 6 miles deep out in the channel. So I mentioned that seismographs weren't actually developed until the 1930s and actually used, but there is a recording of the Santa Barbara earthquake that was a temperature measuring device from the Southern County's gas company. So, that you can see that there was a little disturbance kind of in here in the middle of the night. This is 3 a.m., so 3:30. And then here's where we get to the big, activity, which was, 6:40. It's kind of neat to be able to actually see it. And again, that 6:40 was important because, the downtown corridor is really what saw a majority of the catastrophic damage. But not as many people were living in the industrial or commercial space, and so they were at home, and we'll see some damage of residences, but they weren't as catastrophic and life concerning. So here's a picture that I could have picked out of almost any earthquake that in the past. Here's Long Beach right after. Here's Alaska, 64. Here's Nisqually, which is up in Seattle area, and Napa just 10 years ago. So they're all very similar in that there's debris fallen right in the road. So we'll talk about what that kind of comes from, but you could see the same thing kind of over and over. Okay, so we're going to talk about URM. So this is a big thing. So unreinforced masonry is what that stands for. So that's brick, that's stone, that's adobe that doesn't have steel rebar reinforcing it. So here's just a quick primer on the types of failures that we're going to see, because we're going to see a lot of them just over and over. So out of plane wall, so that's a wall like this one behind us. It's attached to the floor, it's attached to the roof, and it's shaking out of plane with the weight of it. So a masonry wall is really heavy, and so it shakes and then it pulls away and it fails like that. Out of plane anchorage, so the wall is attached to the floor, it's attached to the roof, and if it's not attached well, then it can pull away and lose support of the roof. Out of plane parapet, so the parapet is the flat roof, and then there's the wall that comes up above the roof, right? And so in like these cases, the wall is kind of below the roof, but in that case, it's up above the roof, just hanging out there, just waiting, and for an acceleration to send it over its edge. So we will see a lot of those out of plane parapet failures. This is actually showing retrofits. So we'll talk a little bit about retrofits later, but basically what you do is you come in and make a strong connection to the base of the parapet, and then you also would tie the floor or roof actually really well to the outer wall, which is the retrofit of this. Right? So one thing also to kind of pay attention to would be like these joists this would be like the rafters in your roof. And so they run either parallel to the wall or they could run into the wall, right? So if they run into the wall, then the wall is what's supporting the parapet, or the wall is what's supporting the roof, sorry. And then in-plane shear. So in-plane shear is this wall. So these walls have done their job and they brought the load up into this floor, and then that brings it over here, and then this wall is shaking kind of in plane like this, and that overall is what resolves the forces in the earthquake. So you can see diagonal cracks. We'll see a lot of these as well. That's the wall racking back and forth and kind of creating that diagonal cracking. So this was shared with me. This is really cool. After all earthquakes today, people go out and survey the damage and try and learn something. And that happened, in the days following the 25 earthquake as well. So a handful of engineers came and looked over the damage and then made some observations. So I'll read this for you. Our inspection of damaged buildings leads us to the conclusion that much of the damage might have been avoided if better material and workmanship had entered into the construction of the buildings affected by the earthquake. Wherever good materials have been properly used and the design has been an intelligent one, slight damage or none has resulted. Brick, tile, and concrete block construction have proved unsatisfactory in most cases, which have come under our observation. Even so-called reinforced concrete has failed when of poor workmanship or design. As a matter of record, we note the absence, but with two exceptions, of steel frame construction. They came through in grand shape. So here is, a picture looking north of State Street. The Hotel Californian is, a big noticeable site. The railroad tracks coming through here, the train station there. This is San Francisco after the 1906 earthquake. So 20 years earlier, there was a big earthquake. This is, like I mentioned earlier, the biggest earthquake that California has seen. But the bigger thing was the fire. So after the earthquake, gas lines broken, people accidentally starting fires. And so I think like 80% of the damage was actually fires as opposed to earthquakes.
No water.
And no water. So for our earthquake, we had some, Santa Barbara heroes that were at the different utilities that shut them off as the big earthquake happened. So you shut off the utilities, and now we don't have gas leaking everywhere and starting fires. And electricity, we've seen what electricity can do to create fires. So we'll go into some of the specific buildings. Here's the Hotel Californian. This is, if you've seen a picture of this earthquake, this is probably, the building that you've seen pictures of. It was, constructed or opened not long before the earthquake, actually, but very quickly turned to this because of just the standards of design that we had at the time. So you can see, obviously, the walls pulled away. You can see some of the diagonal kind of cracking that we talked about. But the big failure, which we're going to see kind of over and over again, is that the walls, pull away from the building structure itself, right? So each of these guys, is a floor joist that was kind of supported, by that wall. There's a couple more angles to that building. Kind of the same diagonal cracking of this, probably pulled away and just folded off the building. Over on this side, you can see kind of the diagonal cracking kind of here again. And then probably there was ornamentation here that was heavier than the surrounding area and fell off. So here's another building. Again, very similar, right? But looks like the front just peeled right off. So you can see on the side over this side, there's, brick, and it's just gone in the front. All down here on these crushed cars. So that's the, probably the same area is about the same weight as this, right? So there's a lot of weight in that unreinforced brick that was, on the facade there that pulled away. And it looks like, so here looks like, there was a floor across here and a roof that would have been up higher. Looks like what would have been, a deck or something out here. But obviously, as this collapsed, this kind of follows it. Here's a building on Rio, the site of the current Canary Hotel. So this site eventually was, demolished when that hotel was built, but this is how it came through the earthquake. What's interesting about this one, I think, is that you can see, the concrete frame. So these are concrete, and then you can also see some brick kind of fell out from in between. In the background over here, you can see that diagonal crack through the window there. You can see the ornamentation here that just, was pulled off of the building. But this is, a picture of that concrete building that was constructed well. It saw damage, but it held up here, right? All the people that would have been up here, safe to get out. So public library, same idea again, right? We've got heavy brick, would have been unreinforced, that just peeled away there. You got a partial collapse of the roof that would have been bearing, on the masonry that fell off. And then I love about this picture over on the left there, if anybody read the Mike Mulligan Steam Shovel, it reminds me of that book. So this is a picture of the telephone building. You can tell because it's being propped up by telephone poles. And again, it's the same story, right? So unreinforced brick. Parapet that was up here, that's the top of the roof, is gone. So it's pulled off and fell. Diagonal cracking here. The parapet up here fell. All of the rubble down on the bottom, ready to be cleaned up. This one I think is interesting because at first glance you kind of see three different buildings or three different regions. First glance, right? Whoa, this one saw a lot of damage. And then this one, yeah, there was a ton of damage pulling off here, but at least it's still standing, right? The floor's there. And then you look at this one, and kind of at first glance, you think, oh, there's nothing much happened to that one. That's kind of amazing. Then you kind of start to look a little bit closer and realize, oh, well, that's the roof of this building. And this is the parapet that used to be up there. So that just big thing just fell in one big chunk and landed down on the bottom. And then probably the difference between this building and this side over here is that all of these joists, all these rafters are pointing toward the street. So they would have been supported by this wall. Whereas the other side is probably, parallel to the wall. So the wall fell away, but the joists could remain. So there were some good stories too, right? So The Balboa building, which is, current day, looks very similar to what it was before, but here's a picture of damage that happened on the Balboa building. And this is very stereotypical concrete failure of a concrete shear wall building. But this is how a concrete building dissipates that energy, right? So the earthquake jolts a big, jolt of energy into the building. And then as it's trying to settle, it needs a place for that energy to go. And so what's happening is it racks back and forth as you get the concrete wall straining one way and pulling a strip out, and then straining the other way and pulling another kind of strip out. So you see these very regular X's across all those type of piers. But again, the building kind of stood and it was able to be repaired, and it was built well. So this is behind, kitty corner to the Balboa building. This is where Starbucks used to be. You can see Casa de la Guerra, yeah, right in the background. Plaster looks like it fell off the adobe. And then all the brick, this is obviously days after the earthquake because there's no rubble on the ground. So, all the facade, though, fell off of that building, but the structure, the stud framing kind of remained. So this is, up close again and kind of looking down, obviously more recent to when the earthquake happened. There's all the rubble. You look way down at the other end, and the Granada is this building right here. So further upstate, this is kind of kitty corner to the Granada, actually. This is the San Marcos building. And it's kind of interesting looking at the two sides of it, right? Like if I cover up this, you think, whoa, like a bomb went off and that whole side is kind of shattered. And then you cover up the other side and it almost looks like it's in the middle of construction, like nothing happened. What it was is it was one building, but it was built as two with a separation, but there's no actual separation. So the buildings actually, I'm sure, probably banged against each other, and then this building lost, and this one kind of remained in place, and the other one, lost its capacity. It probably has to do with, like, I'm guessing there was a corner here that was open, right? Like a storefront on a typical resident or a commercial space, nice and open. And maybe it was more open than this side over here and just caused a weakness. So that's it. Not a colored kind of version of it. But in the foreground is the Granada. So the Granada opened in April 24, so a year earlier, essentially. And I met somebody the other day who said that their great uncle built this building and was smart enough to go up there and put a banner on it after he built it and it stood, and advertise his construction capabilities. So it's since been retrofit in the early 2000s, but you can kind of actually see. I think I read a few things that said there's no damage, but it kind of looks like there's an X in this to me, which would be what you would expect and where you'd expect it. And again, it's a well-built building that was doing its job, dissipating energy. So there it is today. Here's City Hall. Most of you guys are, kids at heart, I'm sure, but maybe don't go to Kids Draw Architecture. Really neat program, and this is my drawing from this last architecture. And I was excited to go back and actually see the City Hall with the shield on the corner from it, so I had to put that in. This is the Arlington Hotel. So this is kind of a story wrapped in fire. The hotel was burnt down in like 1908 or something, rebuilt, and they got really smart and put a water tank up in the tower here to prevent fire, which is right where the majority of the failure happened. It's tough. Can't win them all. And then we have the mission. So, the mission obviously saw damage in the towers, substantial damage in the towers, and this kind of parapet that would have been over the roof. This looks like it's a floor that collapsed, and that probably is from rubble that came down and landed on top of it. The mission was rebuilt just out of stone, just like it was, and then in the 50s was rebuilt with concrete. So the facade and towers are built in concrete. So don't tell anybody outside of this room, but if you look really closely, these aren't actually stones, they're painted. So there was other infrastructure damage. This is the one time in U.S. history so far that a dam has failed due to an earthquake. Sent a flood of water down through the east side, which was mostly kind of farmland at the time. So not, and it wasn't too terrible. That wasn't too damaging or life threatening. And then there's surface ruptures of roadways, railroad tracks. If anybody was around in '78 when there was an earthquake in Goleta, there was a railroad car that tipped off the tracks, and other minimal damage out in Goleta as well. So there's not as many pictures of single-family residences, but here's a couple, and they're very similar. The one on the left, you can see everything is kind of tilted, and the door is actually below the steps. So this fell off of its foundation. Amazingly, to me, the chimney is still there in that one. The one on the right is another similar situation, but you can see the starting of a fireplace here and the ending of it over here. The top chimney, fell off, obviously. The whole building just slid off of its foundation, by 3 feet or so. Okay, so now we're going to follow up in kind of what we've done, how we've kind of adjusted, and what earthquakes have kind of where they've taken us. So this is important earthquakes in California since the 1925 earthquake. So there was a big earthquake in Long Beach in '33, El Centro, which is down San Diego area, in 1940. Silmar, that's San Fernando Valley, in '71. Loma Prieta, that's the Bay Area earthquake, in '89. Northridge earthquake in '94. And these are all 7.6s, big earthquakes, did damage, and we've learned different things from each of them, which is kind of why I highlighted these. Each of these earthquakes has a story just like the one we've kind of gone through here, and you could go really in depth and learn about a ton of stuff just for each of those earthquakes. I think one of the really neat things about the Santa Barbara earthquake is that it actually was kind of a turning point in earthquake design. So prior to 1925, there was no unified building code throughout California, throughout the United States. Each kind of region, each city did it for themselves. So following the earthquake, not that this was the instigator of the whole building code, but the 1927 was the first edition of the Uniform Building Code. And it was 275 pages, and there were 2 pages of suggested earthquake design. So I highlighted suggested right there. That's so the all you had to do was this little bit. But it was the immediate impact or the recognition that we need to actually design for earthquakes, and it's kind of a cool thing for me as a structural engineer to think that the earthquake that was from here started kind of this movement of actually designing for earthquakes. At the time, it was very simplified design, and you just take 10% of the weight of the building and then design it. We've escalated that quite a bit. Long Beach, 1933. So this earthquake is really important. Again, you look at the time. So it was 6 o'clock on a Friday afternoon. Timing was great because it significantly damaged a bunch of heavy unreinforced masonry schools. And so elementary schools, middle schools, high schools all had damage similar to this, but being Friday at 6 o'clock, no kids were there. So the immediate reaction was that the DSA Field Act was created, which was you needed to survey basically all of schools, and from that time forward, schools have kind of been put on a pedestal. So all public schools are specially designed. There's a special agency that reviews everything, and they basically kind of went through and ensured that unreinforced masonry was removed from schools. In the 35, so a couple years after the 33 earthquake, we updated to mandatory. So now we've got mandatory earthquake design, and it was 5 whole pages. But there is this kind of cool map, which is similar to what we've seen already, which is the regions. So yellow is zone 1. You don't need to pay much attention to earthquakes. Zone 2, zone 3. It's since kind of evolved and escalated, but that's kind of the basis of kind of importance in earthquake design. So El Centro, 1940. This is the first recorded seismograph recording of an earthquake. So this shake had been used in a ton of earthquake engineering research. Silmar in 1971. So this is San Fernando Valley over kind of near Magic Mountain. This caused damage kind of widespread and actually caused damage at hospitals. So there was an immediate response. In 1972, there was a hospital act that basically mandated that or recognized that we need to keep hospitals operational. So now in the current design of a hospital, and there's since been laws requiring it, that every hospital has and fire department and police station or emergency operations center is occupiable in an earthquake, after an earthquake, right? So we now design hospitals, schools with a higher importance factor. So we design for a higher level of force. We design for less deflections, so they don't move as much. So it means that all the fixtures and everything inside has less of a chance to fall, because actually the insides of a building, create quite a bit of damage as well. So Loma Prieta, this is like one of my favorite, hate to say that word, but earthquakes. This is actually a picture of a baseball card. I used to collect all the baseball cards, and if you remember that earthquake, it happened during the World Series. Of course, it was the Giants against the A's, which, again, like the story is that because it was the Giants and the A's, it was so local to San Francisco that not as many people were out on the infrastructure. And so there were bridge collapses here, but the damage could have been so much, or the fatalities could have been so much worse if there were, people weren't, going to the World Series and going home to see it. And then Northridge, of course, in 94. So this, is what used to be a 3-story building, now without the first floor. So, each of these earthquakes has different things that we learned. In the Loma Prieta earthquake, we learned about liquefaction, which is earthquake shaking, and then the soil can kind of, they in the Marina district of San Francisco, they bought themselves some more land by just dumping dirt out there. Well, it didn't get compacted, and in the end, it turns into kind of liquid in an earthquake, and buildings kind of sink into it. We learned about soft story buildings, that there's a weak story underneath buildings that really needs to strengthen. We're kind of constantly learning. One of the themes, of course, is what was mentioned in the original document that I shared about the people who came and inspected the buildings was good building materials, and good design make good buildings. I was able to actually go to the earthquake in Haiti in 2010, after the earthquakes. This is probably a month or so after the earthquake. The middle is a typical picture that you'd see in any earthquake in any kind of developing country, that hasn't developed, kind of our United States or Japanese kind of level of engineering. Heavy buildings, because that's what's available. One of the cool things that I was able to do is I was able to go around with this guy who was a Haitian engineer, learning the trade, was young in the trade, and been designing some buildings. We were going around to kind of random places, and doing survey of buildings, and being able to tell people, you need to fix this, or this is kind of how we need to do this. And it was pretty rewarding in times when you could actually tell people, like, well, this building actually looks good, because some people, or a lot of people, the first instinct is, I'm not going back in my building, right? I'm going to go stay in a tent outside. And there was tents, if you remember any of the pictures, throughout Haiti at that time. But the neat story with this is that this is the owner, and it was a building that he designed, that he actually oversaw construction of. And so he had some quality control in it. A lot of times in Haiti or developing countries, you might, cement's the most expensive material to build with, of how they're building. So you might get a little less cement, a little more sand from the river. And so, when you pay attention to the details and you pay attention to the materials that are going into it, buildings can be safe in any location. Since we, kind of came through these various earthquakes, there's been all these steps kind of in the right direction. So finally, in '86, there was a mandatory unreinforced masonry law. So this was, you have to survey all your unreinforced masonry buildings in seismic zone 4, which is us and a lot of California. And then you have to make a plan for what to do with them. And so as a result of that, some buildings were demolished, some buildings were strengthened, but they kept on it with all of the cities. The state did, and kind of tracked everything. And so by, I think this was a 2004 survey that was all the cities. Santa Barbara had basically addressed, mitigated 99% of the unreinforced masonry buildings that had been found initially. And again, this is the big damage maker, right? That's not the only one for sure, but it's definitely low-hanging fruit. So for residences, California has this brace and bolt program. This is established in 2013, but it's a very simple program. And one of the things, this is going back to those residences that just shake off of their foundations. So the before picture is, there's no connection kind of between the crawl space. This is the floor that you walk on, the crawl space here, and the foundation below. And so adding, both shear panels in front of this, and then anchors down to the foundation, lock it to the foundation. That's one of the known, simple causes that, single family residences, see failures of. Um, both the Loma Prieta and Northridge. I think this is a Northridge photo. This again was a 3-story building that squashed. So this is your typical apartment building with tuck under parking that you hear about. And so there's some cities that have mandatory soft story retrofit ordinances. Los Angeles has it. Bay Area has it, where you have to basically strengthen this weak story by providing a frame that'll resist that force. So we've learned about non-ductile concrete. This is like a bit more complicated, but it's essentially, concrete's really heavy, and if there's not reinforcement placed correctly and sufficiently, then it can be weak still. So this is kind of what we would do today in a current concrete building in a current column versus what would have been done. So this just doesn't have the ductility to allow the building to sway and move, where this allows you to do that. So what could happen is that type of collapse. So again, some building or some building departments have a mandatory ordinance for non-ductile concrete. So Los Angeles, Long Beach, I think Santa Monica. And so this is the end of our tour. We're learning with everything, just like you guys are learning with everything, right? And we're eventually just pushing this battle into, toning it down a little bit. That's it. You made it.
Questions?
Uh-oh.
You haven't mentioned glass.
Glass, correct. I didn't mention glass. You can, but we generally don't build much out of glass.
I was thinking large plate glass windows look like they were reflective in some of your early post Santa Barbara photos.
Yep.
And it looked like in some cases it didn't shatter. Is that true?
In some instances, I'm sure. I don't actually know the details of it, but glass obviously is super brittle, and now you'd have kind of a little bit of give between the glass and the building, and we're double paned, and so there's a little bit more kind of flexibility built into it. But yeah, single pane of glass, big pane, I wouldn't want to be right in front of. Way back.
I want to thank you for the local photos, because I'm a victim of the media, and I think many of us have seen a lot of photos of the San Marcos building and Hotel California, because those are the ones that were splashed all over. But you showed, and part of that, or a concurrent story, is that much of the downtown was destroyed. And we see a couple of buildings again and again and again that were destroyed. And yet what you've shown is really, there was a lot of damage, because you showed not the big flashy building that made headlines on the East Coast, but the real damage.
Yeah.
So thank you very much. You brought a different perspective than I've ever seen dealing with our.
That's great. Thank you. I mean, that was all due to these guys who provided the photos for me.
I would encourage everyone to go to the Historical Museum. Right now, they have a great exhibit of photos of the earthquake. It will only be up until July 6th. So head over there. It's free and a lot of great photos. And one thing that you've mentioned is the tectonic plates moving around out here. In other parts of the country, there are other things that cause earthquakes. I used to live in the Chicago area, and one time an earthquake woke me up in the middle of the night, and I thought, whoa, what is this? But apparently in northern Illinois, during the ice age, it was under miles, maybe a mile or two of ice, and which pressed down on the earth. And now the earth is still a little bit coming back up after having been pressed down.
Interesting. I hadn't heard that.
Thanks for the great talk. Where did the rubble go from the Santa Barbara earthquake, and what's on top of it?
Lower East Side
Yeah.
zone.
Yeah, we're going up Martina. Yeah.
I'm sorry, can you repeat?
Lower East Side is the general consensus.
Yeah.
It was a swamp.
Yeah, where Peabody Stadium was a swamp, right? Yeah. Yes, sir.
So you mentioned the importance factor for hospitals and schools. I know that there's different kinds of criteria for, like, say, nuclear building or things like that.
Mhm.
Following Fukushima, I'm just curious if you can say what standards might be those kind of different special buildings that aren't.
Yeah. Well, yeah, nuclear buildings have their own kind of design for sure, but at the end of the day, it's an emergency operations kind of type of facility as well. So they would have the same type of seismic standards as any of these high end, like the new police station building, right? That building will be designed for a higher importance factor. It will be designed for a reduced deflections, so that when an earthquake comes, that they can still be operational.
Building dampers have enough height for it?
We don't, yeah, generally not. So building dampers, there's like a few really cool things that have been developed as a part of earthquake recognition. Building dampers, which kind of counteracts the shaking up high in the building, or one thing. Base isolation is another thing, which is basically taking the building and putting it on slides so the earth shakes, but the building doesn't actually see it. But those are expensive systems that are for bigger type of facilities.
You see a building, a damper on one of the wings.
Yeah. And there's also at Cottage Hospital. There's they've also started to develop using steel diagonally, so braced frames is like a really efficient way to get forces from up high in the building down, and that's gone through a few iterations of what a braced frame is. One of the cool things that they do now is what's called a buckling restrained brace frame, which is like way over what anybody needs to remember, but there's really cool technology because it just like really dissipates energy by like acting within a core. It's just really cool.
Do you have any advice for architects in general practice how to design with better earthquake systems in mind?
Got to get rid of all the windows. No, I mean, hire a good structural engineer and listen to them when they tell you that's a bad idea. But the building code now identifies like all of the things, we call them like irregularities, and so there's things that you would design for like a reentrant corner, which is like the inside corner of a building that might want to pry apart like that. So in current building design, we're designing for all of those things. That doesn't necessarily mean it's a great idea. The Granada building, the Balboa building were effectively like boxes, right? And so that's not the most exciting architecture, but it certainly is a kind of resilient kind of geometry. But there's so much that engineers can do. Cass.
Well, thank you so much. So interesting, and looking forward to this. Brought up a lot of really interesting aspects. I have two questions. One is about just thinking about what this young lady just was asking about, design, and then of the shape of the building to have a safer building from earthquakes, and also about the materials using and sustainability, because concrete and steel are, from a sustainability point of view, not good materials. A good plan.
Right.
Wood is light, and, you know, it's the rock, scissors, paper, isn't it? You know, which one is, uh, which are superior materials, thinking of all of those things.
Yeah.
Maybe could you talk about that just a little bit, and then I have another.
Okay, yeah, sure. So materials-wise, I will say that for timber specifically, they're starting to do really cool things with what's called mass timber. So you can picture a sheet of plywood, 8 feet by 4 feet, and then upscale it. You know, so it's now 20 feet by 10 feet wide, and 4 inches thick, 6 inches thick, however thick you need it. And it's a lamination, so it's some boards this way, some boards this way, another board this way, another board this way. And so that material is starting to be used actually like in high-rise buildings in other countries at this point. And it's starting to kind of get adopted into United States codes. As both floor systems and shear walls. So kind of replacing concrete, like in a more sustainable material. It's still kind of components, where like concrete, you put all the rebar in it and it's stitched together and it's effectively like one material all the way up, even though it's kind of poured in different phases, right? We can't pour a 30-story building in one pour. You have to go up kind of bit by bit, but it's all stitched together with the rebar really well. Where the mass timber is, connected and interconnected with connectors. But it's a really cool product. And actually, thinking of the police station is, I think, going to be the first building in town that's going to have some mass timber in it. It's going to be the floor system. It's not the lateral system. Second question.
Yeah, this is different. Thinking about the San Andreas Fault, so we have these plates, and the picture you were showing, we can see the San Andreas Fault, that's the big one, right? And then there's all these others.
Yep.
So how does that work? These like fracture lines or something? What
yeah, basically. So we need to get our geologist to really effectively answer that. But yeah, I think that all of the primary fault is that San Andreas, and that's the plate line, right? So that's the difference between the plates, and then all those others, I believe, are just kind of stress lines that have developed, over time.
Are there any recycled plastics coming into use? In other words, instead of throwing the plastics away, whatever, is there anybody developing way to use plastic or reusing it in construction?
Yeah, but they're not so much structural materials at this point. So you think of like wood decking, like Trex, Trex or TimberTech or any of those types of materials. And there's similar other products that are being used actually in like in some like marine environments and nuclear. There's some like polymers used for like some materials, that are kind of corrosion, resistant. So there are some materials like that. There's some like repair, like you can use like a polymer, like a carbon fiber or a fiberglass wrap to repair some things. And so that's like a glued on blanket that you can use to strengthen. And so there's things like that, but there isn't really, and there is actually fiberglass reinforcement that's kind of starting to be used a little bit in place of steel reinforcement, but it's more so for non-structural applications. So like a slab on grade or something like that that isn't carrying really heavy, loads like this for building.
If there's ever an earthquake in the future,
there will be. There was probably one.
To go in the building. Is it the door threshold? You hear all these things.
Yeah.
You should go outside. You should stay inside.
Right. Right. Yeah. I mean, we teach our kids in school to go under something, right? We teach our office to go under something. So it's really the initial kind of thing is to protect yourself against falling objects from inside the house. So it's finding a safe place for that. So it could be a door. A door is not a bad place to be. Under a table is also not a bad place to be. You know, the don't run outside is the like thinking of the pictures of the parapet falling. You know, all of those are right above entrances and exits, and so that's what you don't want to necessarily kind of fall. But like
But in a neighborhood like this,
yeah.
Okay,
You shouldn't, but you, again, like in a neighborhood like this or residential neighborhoods throughout, like the fall hazard is the chimney, right? So you'd want to be aware of those heavy things up in the air,
In Japan, they go to the doorway and open the door, because often the door can get jammed as the building is shifting, jammed shut.
Back in the sixties, I spent some time in Colombia, and they have enormous bamboo there. It's not like what we think of.
Mm-hmm.
And they do a lot of buildings in the hot country with bamboo.
Yeah.
And they're very successful because they absorb the pressures that are happening all around.
Yep.
And I was amazed that many of the buildings in severe earthquakes break when it was over.
Yeah.
It just fell over in there, but
Yeah.
and the other thing is, of course, they don't in the hot country. There are two windows. Open.
Mm-hmm. Yeah, bamboo is a very strong material, for compression. And there's buildings across the world that are built of bamboo. Definitely, there's a business here locally that puts up temporary structures that probably will be, at the solstice parade. I'm guessing, over the weekend. But he, has bamboo sticks that are, 15, 20 feet long, and he kind of lashes them together, and builds little structures out of them. One more.
Yes. I'm curious if you know offhand or guess when like the soil period matches the frequency of the earthquake, you get the resonant kind of condition where it amplifies the amount of shaking that's happening at a certain height building.
Yeah.
We saw that like with the Mexico City earthquake. Buildings 10 stories high fell down. I'm just curious if you know what maybe the height would be for Santa Barbara kind of conditions. That would be
The toughest question for the last. I shouldn't have asked you.
You don't have to.
I don't actually know the answer to that, but the root of the question is that the soil dynamics, affect building structures, right? So hard soil versus soft soil versus liquefiable soil, and there are a ton of different actual conditions throughout Santa Barbara that vary, right? So, like we said, the downtown, there was, there's some bad soils, quote unquote bad soils. Out by the airport, there's some bad soils. There's some decent soils as well. Oh, we got another. Okay, we're never gonna get out of here. Yes, sir.
Yes. How many people died in the 1925 Santa Barbara earthquake?
11.
11. Yeah.
Okay. All right. Well, those were all great questions, and Sage, you handled them well. Presentation.